I just want to introduce you in Turkish, and then Tuğcan will speak, and then we will let you do your presentation. And thanks again for accepting our invitation.
Okay. Metin Hocam sağ olun, teşekkürler.
Rica ederim Emre Tuğcan Bey. Biz teşekkür ediyoruz bu güzel etkinlik ve katkılarınız için.
Rica ederiz.
Ben çok kısa bir şekilde Doktor Braak'ı Türkçe olarak tanıtayım. Kendisi mineral işleme ve metalürji endüstrileriyle ilgili yenilikçi çözümler geliştirme konusunda deneyimli, yetenekli bir süreç ve yazılım mühendisidir. 2018'den beri CASPEO'da önemli çeşitli görevlerde bulunmuş, önemli katkılar yapmış. Inventio yazılımı ve USIM PAC süreç simülatörü için yazılım modüllerinin belirlenmesi ve geliştirilmesine öncülük etmiştir. Ayrıca endüstriyel tesisler için metaliklerle ilgili çeşitli muhasebe çözümlerinin uygulanmasında, operasyonel verimliliğin ve hassasiyetin artırılmasında önemli bir rol oynamıştır. Ayrıca Dr. Braak, CASPEO'nun H2020 iTrends projesi de dahil olmak üzere birden fazla araştırma girişimindeki katılımını yönetmiştir. Kusura bakmayın, ben biraz İngilizce olan yerden çevirmeye çalışıyorum. Tuğcan Bey, eğer eksiklerim veya yanlış söylediğim bir şey olursa lütfen sizler müdahale edebilirsiniz. Bu anlamda katkıları su arıtma süreçlerinin modellenmesi ve geri dönüştürülmüş suyun metalürji operasyonları üzerindeki etkisinin değerlendirilmesine odaklanmıştır. Dr. Braak, IMPT'den sanırım Toulouse Ulusal Politeknik Enstitüsü süreç ve çevre mühendisliği alanında doktora ve École Centrale Lyon'da mühendislik derecesi almıştır. Çalışmaları mühendislikte inovasyon ve sürdürülebilirliği olan çeşitli güçlü bağlarını da yansıtmaktadır. Evet. Tuğcan Bey buyurunuz. Ben size sözleri veriyorum. Ardından da sunumumuza geçebiliriz.
Teşekkürler Metin Hocam. Sağ olun. Hoş geldiniz değerli katılımcılar, meslektaşlarımız. Çok kısaca bir giriş yapayım. Yani vaktinizi çalmadan. CASPEO firması bizim teknik partnerimiz. Geliştirdikleri programları kullanıyoruz. Zaman zaman geliştirmelerine yardımcı oluyoruz. Beraber etkinlikler yapıyoruz. Burada benim vurgulamak istediğim şu. Bu modeller genelde prosesi anladıktan sonra hani kabaca ölümsüzleştirmeye yarayan, biz deneyimizi yaptık, bir daha deney yapmadan aynı parametrelerin farklı değerlerini deneyerek ne sonuç çıkarın cevabını veren çalışmalar bildiğiniz gibi. Hiçbir zaman gene vurgulamak gerekirse deneyler alternatif değil. Deneylerin bütünleyici ve tamamlayıcı unsuru. Yani deney ve her zaman model birliktedir. Onun dışında bir modelin temsili ve basit olması her zaman bizim isteğimizdir. Yani matematiksel olarak çok karmaşık 10-15 parametreli bir model istatistiki olarak her zaman doğru sonuç daha fazla verir. Fakat temsiliyeti ve fiziksel temsiliyeti her zaman tartışılır. Bu anlamda CASPEO'nun, Etienne'in hani içinde bulunduğu, geliştirdiği bu model aslında bir anlamda kualitatif bir şeyi de modelliyor. Yani yüzey kimyasında belli parametreleri, belli fiziksel çokluklarla modelliyor. Bu değerli. Yani hani direkt 3 artı 5, 8 gibi bir şey değil ama hani flotasyonda su etkisini modellemek, yani yüzey kimyasını sayısallaştırmak biraz daha hani sıkıntılı bir iş. O yüzden yani güzel bir çalışma olduğunu düşünüyoruz, biliyoruz. Sözü arkadaşımıza bırakalım daha uzatmadan. Etienne, it's your turn.
Okay.
We just mentioned quickly the model should be representative and simple enough to reflect physical reality. And that's your model. That's your improvement, your and Caspeo's improvement. And also reflecting surface chemical or physical surface chemistry properties in mineral processing is not an easy job, but this is what you have been trying to do in this model. So thank you. Go ahead, please.
Thank you very much for the introduction, and thank you to YERMAM and MPES for hosting this webinar and giving the opportunity to discuss about the effect of water quality on flotation performance and how to simulate this on a steady state simulator. So we will see that with USIM PAC commercial software. So we will begin by summing up the background, go through the methodology so to build the simulator embedding the water effect on flotation performance, and so see how to implement it in a software and illustrate this with a demo, and finally go through a case study of a copper nickel concentrator. Most of the work that will be presented in this webinar was made in the European Union project ITERAMS. So it had several targets: tailings valorization, minimization of environmental footprint, and have a more efficient water recycling in mineral processing plants. And so this is in this task that Caspeo was involved, and more precisely in process simulation. So to give a big picture about water management and the necessity of the company to have good water stewardship to maintain or earn a social license to operate, there is a need. What I want to illustrate here is there is need to make water reporting. So this can be made in several levels. At the smaller level, at mine level, so after Brumadinho failure tailing dams, we had the global industry standard on tailings management that was released, and it embeds the need for the requirement for water accounting on tailing dams. At the company level, so we have several frameworks, the water accounting framework and the water reporting, that enable to make gave the framework for every site and gives the possibility for the company to gather all this data in the same report. And in this way, the company can communicate on the way it manages water. Water management can be embedded also in higher level reports that regard more sustainable development in frameworks such as Carbon Disclosure Project or Global Reporting Initiative. What is important here is that there's a global need for water reporting, and this need leads to the need to decrease the raw water intake, and consequently to the need to recycle more water in the plants. And this increased need of water recycling also arises from a processing point of view. So water is recorded both as transportation media and reaction media. And with the decrease of the ore body head grades, we have a larger amount to treat, and so a larger amount of water to treat the minerals. So there's also a general trend to increase the water recycling, which leads to more charged, recirculated processed water. And two questions arise. What is the impact on the process performance, and how to manage this impact? So here is a simple flow sheet to illustrate the configurations that we can encounter, and it illustrates our case study so we have grinding, copper and sequential nickel flotation, and the tailing ponds at the end. So the slurry goes to the tailing ponds, it settles, and with this natural settlement, we are able to have to recover some water and recirculate it through the different stages of our plant. But we still need an input of fresh water. Another configuration that we could encounter is recirculation before tailings. So here, this is our case study, but modified a little by introducing solid liquid separation after each flotation stage. And so we are more, let's say, in a dry stacking configuration with more dry tailings, but we are able to recirculate selectively water dedicated to each flotation circuit with the corresponding reagent. We still need an input of fresh water. So this has the two big configurations that will be discussed about in the in this webinar. If we go on more detail to illustrate, here we have the description of the copper flotation section. So with the grinding, the different stages of flotation, roofer, scavenger, and cleaners, and the other operation. So we need to model all this a solid liquid separation unit to recirculate some water, eventually to implement some water treatment on the recirculation. Now that we recirculate water inside the plant, we have to account also for the mineral dissolution that occurs inside the plant and not on the tailing pond. And so here we associate it with every unit operation where the dissolution of mineral can occur, so grinding and flotation, and finally our flotation stages. So to give a bit more information, more information on the water quality variation. So the main problem is mineral dissolution that increase the concentration of dissolved components, which can impact flotation and can lead to the requirement of water treatment to maintain water performance. So we think we have in our two configurations, in fact, we have two kinds of dissolution. What is called the long-term dissolution that may occur in tailing ponds, and is more dependent on environmental conditions. So this is what is illustrated on the graph. It represents water quality variations depending on time, and it is for so a Copernican plant located in Lapland, so with very cold winter. So we see that a long time we've got a general increase. So this is the conductivity. We've got a general increase of conductivity, which is a proxy for the concentration of dissolved elements. But we also see that we have got seasonal variations. In fact, during winter, there's an ice cap. Snow accumulates in this cap, and at spring, when it melts, we've got the melting of the snow, which make water, and dilute the processed water, which accounts for this decrease of conductivity. So we see that depending on the months of the year, we won't have the same water quality, and it will impact the performance of the plant. The other so dissolution behavior is short-term, and it occurs inside the plant in the unit operation, and here it will be more dependent on operating conditions. And this will be more the kind of dissolution that we will tackle in this presentation. So now to tackle this issue of simulation of water impact on the performance, so we will illustrate this by using so steady-state simulator USIM PAC. So this embeds a library of state-of-the-art mineral processing models. What is important here, a specific approach of this software, is that it enables very configurable characterization of material, and it's very suitable when we use complex mixture, as it is the case here with the slurries, which are difficult to describe as pure substances. One other important feature of the software is a new feature we call configurable parameter law, and it enables to integrate easily empirical results from so lab tests or pilot tests in the simulation. And this is we will see that this is important with this semi-empirical approach that we have to tackle the issue of water impact simulation. The simulation advantages are that it avoids costly trials and enables to easily assess new configuration of the plant. So I will now describe the global this approach. So we begin with our configuration of the plant or flow sheet, and what we want is to have predictive mass balance, and depending on the operational conditions. For that, we need a calibrated plant model. For this calibrated plant model, we need the plant data, the size of the equipment, data set to calibrate the model, and the structure plant model. So to build this structure plant model, as discussed, we need a set of unit models that represent that are used in the plant, which will be calibrated with pilot or lab tests, and will be integrated with the description of material in the structure plant model. We will also have a few words about the obtention of the data set for calibration, which classically goes through sampling campaign, data reconciliation, and some assumption on missing data. But now we will focus on the building of the structured plant model. And we will begin with the unit operation models. So unit operation models, basically, it has several inputs. So an input that are regarding the material, so the flow rates, the composition, mineral or chemical, and as input, it has also some parameters, for example, flotation or dissolution kinetics, performance, and the size of the equipment. It gives as outputs the flow rates with mineral and chemical compression, but also some other parameters such as energy consumption and also capital costs. In USIM PAC, we have several levels. We have a specific classification of unit operation models with several levels. So we start with what we call level 0 models, which are pure performance model, just taking into account the results of lab tests, let's say a percentage of removal of a component, but no size parameter. Level 1 models integrate size parameters with simple parameters, but do not require complex experimentation. And we will focus on these two kinds of models. We also have a more complex model with higher accuracy, but which require very specific tests. And I will now start with the first unit operation and the cause of the problem, so the dissolution of mineral. So here in this simple flowsheet is represented an experiment that was made by our partner to simulate the behavior of mineral dissolution inside the plant. They took fresh ore, ground it, pass it through a flotation cell, but without reagent to simulate flotation, but to have the dissolution behavior, filtrated the slurry, so recovered some water for sampling, and so to compensate this loss, took back some water from starting and recirculated this water on grading and dissolution. And so this is a closed cycle, and in several, this is in batch. And after 8 dissolution cycles, so they didn't see much difference on water composition. So to simulate this experiment, we used a first order kinetic model, so with 2 parameters, the kinetic constant and the maximal concentration that can be reached. And so integrated in a continuous process, we use the equation, the corresponding equation, but for a continuous process. So in this graph are presented the results of the experiment and the model calibration. So the results of the experiment are in dot for the first, third, sixth, and eighth cycle. So we see that we reached a limit. But when we calibrated our model, we saw that in fact we could have gone further in concentration. We expected to reach higher concentration. And we explained that, but the fact that this is due to the fact the way the experiment is done, we have to re-add some water at each end of the cycle because we have to compensate the loss. And so we have some dilution each time. And so in fact, this dilution is compensated by the dissolution of minerals that occurs during the batch cycle, but we can't go further. So this is a kind of pseudo-equilibrium. So this dissolution model will be, as presented, previously associated to the unit operations that where dissolution of mineral can occur. We have 3 flotation stages, roofer, scavenger, and cleaner, and we didn't assume dissolution in this stage because the parameter of the tests, in fact, there is a different operating condition in the cleaner with an increase of pH to depress nickel. And so the conditions are not the same as in the flotation test of the plant, on which was based the mineral dissolution test. So these are not the same conditions, and we assume that dissolution did not occur in cleaner. This assumption is reinforced by the fact that most of the slurry stream goes through the roofer and scavenger, and there's not so much slurry that goes through the cleaner. But now let's go through the flotation modeling. And just a few words about flotation. So this is a very complex process that involves many mechanisms, which are try to be synthesized in this graph. So we've got the operating conditions in the flotation cell, so pH, temperature, ionic strength, and water composition. And we can have mechanisms that can be linked to the solids, both valuable and the gang, so oxidation, dissolution of mineral, disruption of reagents, interactions with air bubbles, with disruption of reagents, and with microbiological species also. So this is very complex, and the approach we took was to have a semi-empirical approach, and in fact to embed of this mechanism in more simple model. And we use the first kinetic order model, as we will see.
Etienne, there are some comments. Would you please speak a little slower for Turkish audience? Little.
Okay.
Thank you.
Okay. Sorry. So.
That's okay. Thank you.
So just presenting the experiments that enable to calibrate the models. So batch flotation tests were made with distilled water, dissolution loop water that was produced by the experiment on mineral dissolution at the 8th cycle, and plant process water. So what was seen that comparing distilled water to dissolution loop water, so without reagent, we've got here in white the starting water, distilled water. We've got higher recovery than in dissolution loop water. So negative impact of mineral dissolution, and we considered calcium sulfate and magnesium. And comparing this dissolution loop water to process water, we see a positive impact, better recovery, which is attributed to the positive impact of remaining reagents on the process water. And we integrated all this in flotation kinetic law, as we can see here. So above is presented, recall the first order kinetic model with two populations, floating and no floating. So with two parameters, the ultimate recovery and the kinetic constant. And so to make the model, we made an assumption to simplify the things, and assume that the water impact was mostly on kinetic constant. So finally, the job we had to calibrate the model was to define the kind of flow that is presented below, sorry, with taking into account the concentration of the components that were assumed to have an impact, so sulfate, magnesium, and calcium for negative impact, and collector for positive impact, and so variation of kinetic constant depending on the concentrations of these components. So we've got our cause, the mineral dissolution, we've got the impact on flotation, and now we'll go through the last unit operation we need to mitigate the impact of mineral dissolution, so water treatment units. So they will be implemented on recirculation streams. They will induce cost with capex and sizing of units, and also OPEX, so with reagent and energy consumption. And we will see two unit operations here, disordered flotation and ion exchange resins. So disordered flotation is more as target components for fines and dissolved components. So it has a pretreatment with coagulation flocculation. And after this pretreatment, pressurized air is released to produce microbubbles that will aggregate with flux, make them float, and they can be removed. So the model is quite simple. You use USIM PAC. We have got a fixed performance and key parameters, so air concentrations and length width ratio. And with that, we are able to calculate outputs, main characteristics of the process, energy, and reagent consumption. The second unit operation is ion exchange resin. So the targeted compound here is sulfates. This is sulfates are removed by adsorption on resins, and this is a semi-continuous process with adsorption cycles and regeneration cycles. So modeling this time is made with Thomas model with two parameters, kinetic adsorption kinetic constant and resin capacity. And it is obtained, this calibration, with breakthrough curve. So the experiment to have this breakthrough curve is simple. We take our water to treat, pass it through the column and monitor the sulfate concentration at the output. And we obtain so this kind of graph. In blue, we've got the experiment point. And in orange, so the calibrated model. And after in USIM PAC, so we define a concentration limit at the output of the unit, which enables to define the cycle time. And by integrating on the cycle time, we are able to define the residual sulfate concentration, that is split all over time, and the adsorbed concentration of sulfates. So going back to our methodology, so we got all our calibrated unit models now. And I've just will have a few words to obtain the data set for calibration of the structured plant model. So a few words about the sampling campaign and so this whole obtention of data set. So this is a plant where there is a very high water reuse between 86 and 97%. So we sample solids to have the performance of the plant, and it's important to have representative samples. And what was an important output of the project, Iterams, found by our partner, was that the protocols that are usually dedicated to environmental analysis were not suitable for the process waters. And so there was no much confidence on the water component analysis, and water balance was only quantitative in our approach for calibration. And we considered the process water composition. And so we had also to make some assumption, because we're never able to sample everywhere on the plant. So for example, on the cleaner stages, in fact, the flow sheet I showed, we've got one stage, but we have in fact several stages, and we were not able to sample between the stages. So we made the assumption that the kinetic was the same in every well. So having our detailed mass balance and calibrated unit models, we will gather all this, and we will see so we'll now see the demo with calibrated unit models, integration and definition of a material model to have structured plant models. And go to the calibrated plant model. That is our final target. So I will now launch the demo. That is the video. We will now see how to integrate all the presented elements in USIM PAC, a commercial steady-state simulator software. The first step is to draw the flow sheet, which is the structure of our simulator. This is done with a dedicated interface. Several libraries of icons that are associated to the models of software enable to draw the network of nodes and streams that represent the flow sheet of the plant in a meaningful way. The second main step is the description of the material that will be handled in the simulator, which is done with a feature called phase model. First solid phase represents the ore. It is composed of copper-bearing mineral and gangue, which have different floating ability. We have here two proportions to handle floating and no floating. Liquid contains the various ions that were considered as impacting flotation, sulfate, calcium, and magnesium, as well as the reagents for flotation, collector, depressant, and frother, and for water treatment, coagulant and flocculant. The last solid phase is added to manage the flux that can be produced during water treatment. In this case, we consider a fictive copper flotation plant with a simple structure, reverse scavenger, and cleaner stages. Processed water comes from the tailings and is distributed all over the plant. has a reference composition of 620 mg per liter sulfate, 65 mg per liter magnesium, and 160 mg per liter calcium. To account for mineral dissolution, a fictive reactor is associated to the unit operations where dissolution can occur, grading and flotation. The parameters that were determined from dissolution loop lab tests, maximum concentration and kinetic constant, are input of the dissolution model. The flotation properties of the minerals are set in the input stream of the plant. We can set here the ultimate recovery that has been estimated from batch flotation tests. For each flotation stage and each mineral, we integrate the law of flotation variation depending on water compositions that were determined from batch flotation test series with a specific feature, the configurable parameter model. The coefficients that were estimated are set in the specific interface, which enables to make the link with the other parameters of the simulator. For example, here is the coefficient corresponding to the sulfate concentration of the input stream of the rougher stage. Let's now run our simulator. Once the simulation is over, we can save our file now a reference mass balance that enables to calculate performance such as recovery in this configuration. Let's now assume that there is a buildup of dissolved components in the process water. As we saw previously, this can happen with seasonal variations and changes of environmental conditions. Let's save. We'll start from our reference simulator. Save it as another file. And change the composition of the input process water. Let's consider a buildup of around 10% for each impacting component. Let's now run the new simulation. We can now compare the results of the two simulations. First, the recovery of the copper mineral relative to the OFID in our first file. And let's get it from the second file. So we can see here that we've lost around 0.8% in our recovery of copper mineral. To remedy this situation, other treatment operation can be implemented. Let's check flow data to have an idea of the process water flow rate to be treated. We've got 1000 cubic meter per hour in input, and around 550 remaining at the output. So around 450 cubic meter per hour to treat. We've got to treat sulfate, magnesium, and calcium. Unit operations that are considered to do so are dissolved flotation and ion exchange resins. Some calculations should be done before initializing this part of the simulator. Dissolved flotation is the only operation to treat magnesium, and sizing will be based on its performance on this component. It also serves as pretreatment for ion exchange resins, which is needed as a polishing step for sulfate and calcium. As dissolved flotation removes an important ratio of magnesium, if it were used to treat the whole stream, the output magnesium concentration would be lower than the target one. Consequently, only one fraction of the input stream should be treated. Based on this, the target concentration at the output of ion exchange resins operations can be calculated. Here is a subflow sheet corresponding to the established pre-calculation for water treatment. We first have a splitter to manage the bypass of the water treatment operation. We find back here the values that we calculated in our Excel file. Dissolved air flotation comes with a coagulation flocculation pretreatment. The operation model is a performance model, directly considering component removal obtained in pilot tests. Ion exchange resins calibration is based on breakthrough curve tests, with obtain of resin capacity and adsorption kinetics. The number and size of the columns are set as input of the model. A finite mode manages the mixing of bypassed water and treated water. Let's run the calculation. We can check that our target water composition is reached. We can also check the adsorption cycle time. And check whether it is long enough or not. With the sizing of water treatment, we now have a comparison between a loss of performance. With this sizing step, we are now able to compare the loss of performance and the requirement for water treatment. Okay, I will go back to the presentation. So we saw in the demo finally how to obtain the calibrated plant model, and we'll go on the final step of the webinar with assessing different scenarios by modification of the operational conditions to obtain different mass balances and so assess different scenarios. So the first one regards the long loop that was presented at the beginning of the webinar, and with water recirculated from tailings. So in our simulation, we didn't simulate the what occurred in tailings, just considered process water composition steady, and try to see how it impacted the flotation. And we implemented water treatment on this loop to make the comparison of performance. So the calibration was based on lab and pilot results based with real waters and water treatment tests associated to batch flotation tests. So what these tests showed, the results were that we had higher kinetics both for copper and nickel, and so higher recoveries. So we integrated these results on the calibrated the calibrated plant. And we saw that with this more important kinetics of nickel reported to the copper concentrate, and this was a loss of selectivity and of performance. So what we thought is that, in fact, we didn't take into account the depression in the cleaner stages. I recall the flow sheet here. We've got a roofer scavenger, and cleaner. And so, as I already presented, the pH is very higher in cleaner to depress nickel. But this is not this was not embedded in the protocol of batch flotation tests. So we tried another scenario and considered that there was no kinetic variation on the cleaner. Considered that the operating conditions prevails over water variation, and consequently that in this scenario, it's a limiting case where nickel depression prevails in cleaner stages. So here we don't have kinetic variation, selectivity is kept, and in this case we saw an increase of performance. So we see that it's important to integrate the batch tests on a global, to have a global approach on a global plant to have an idea of what will occur. And here, so more advanced work would be required. Another important thing that was highlighted is that in this study was that so we have different unit operation for water treatment, but they don't target the same compound, and they don't have the same. So for distributed flotation, we studied fines and other components. For ion exchange, no fines. So usually, distributed flotation is used before ion exchange. But what is important is to have homogeneity in the protocols for every unit operations. So the second case study regards the recirculation before tailings with short loop configuration, and we will focus on copper section. So we have our CD liquid separation at the end of the copper section with recirculated water dissolution, and we will try to see what occurs when we have more or less intensive solid liquid separation. So this is the percent of solids in the underflow, the solid concentrate of this operation. And we will see how the concentration of sulfates varies on the recirculation. So we initialized with reference process water with sulfates concentration of 620 milligrams per liter. And in this graph, we have the impact of the solid liquid separation underflow, so solid contents, from 45 to 85. We've got in blue our water recirculation ratio. That is the percentage of water that is recirculated inside the plant, and we go up to 95%. And our sulfate concentration. And we see so that the impact of the concentration of sulfate increased with the recirculation intensity. And what is important is that so the calibrated value of maximal concentration was 2,660 milligrams per liter. And here we just reached 1,200, wow, less than zero. So pseudo equilibrium is reached. And now, so to go further, we took the limited case where we recircle the most water with 95%. And so still we have a dissolution or flotation that is impacted, and we implemented different water treatments. So we took three scenarios. We wanted to have at the output of our water treatment, so composition of processed water, weak treatment with 25% more concentrated water, and strong treatment with 25% less concentrated water. So first we set performance model to have an estimation of recirculated concentration. We set the output of the water treatment, and we see what is recirculated. That provides the mass balance, and we were able to size the water unit treatment. And here were the final results. So regarding the performance of the plant, weak treatment led to a decrease of recovery of 4.5%, and strong treatment to an increase of recovery of 2.3%. So these figures should be put in front of the requirement for water treatment intensity. And we see that for strong treatment, we need higher capacity for dissolved flotation, higher number of ion exchange resin columns, and we had shorter adsorption cycle duration, so more intensive process. So to make a summary on the case studies, There are 3 points that I would like to recall. So, the first one regards the process water characterization. So, as mentioned, the current methodology is more devoted to the evaluation for environmental purposes, and it was not really suitable for the characterization of more unstable waters, the process waters, and there's a real need for development of dedicated protocols. We saw the importance of the global approach simulation with trends that are not clear-cut from lab pilot studies, and the importance of this global approach for the potential impact of one operation on downstream ones. For example, if some region of solid-liquid separation is recirculated, some flocculant, to the flotation, this can have an impact on flotation, and this is important to have this holistic approach. The last point is in short fluid configuration. So we show that we have a pseudo-equilibrium both at lab and plant scale, and this equilibrium is the key for the water treatment operation sizing. So summarizing now, on the methodology key points, what I would like to retain is the importance of the good basis data obtaintion. And here, that's to recall, but this requires robust sampling protocol to have representative sample collection and to have good estimation of humidity and good characterization of solids. And as mentioned from the output of case study, we need also good water analysis protocol for water characterization. So this regards the obtention of the data. Regarding the structure, we need several model types, so solid-liquid separation for solid and liquid circulation, mineral dissolution, which accounts for water composition variations, flotation, which will give or mineral recovery, and water treatment operations that will make the corrections to water composition variations. And this is by gathering all these bricks that we will obtain the simulator. And finally, what I call exhaustivity of monitoring is what I mentioned. The protocol should be homogeneous between the different unit operations that are studied. Even the point is not at the beginning the focus of the unit operation. This protocol should be the same between every considered unit operation. So all of this enabled to build this methodology that we saw. That was the final result of this project regarding water management. So to conclude, given the complexity of the mechanism involved in flotation, we consider the semi-empirical approach, and this combination of experimentation and simulation capabilities enabled to build a plant simulator that provides mass balances, equipment sizing, and energy consumption, which in turn enable to assess, to have economic and environmental assessment of different scenarios. And finally, we see that simulation through a better plant behavior understanding enables an efficient water use, which in turn enables from the company to demonstrate good compliance with water stewardship. So here are some reference if you want to go further. Thank you very much for your attention. If you have some questions.
Evet.
Gülcan Hocam buyurun, siz devam edin.
Teşekkürler. Etienne, how long did it take the study, including sampling campaign?
The project was 3 years long. It was a bit extended because of the COVID crisis. So
3 years.
3 years and a half. And the sampling campaign were done in winter and in summer to have, as we saw that we had different composition, we made 2 sampling campaigns. But it was difficult to have.
I'm not asking about specific sampling campaign. What I'm trying to ask, this is a big project and there are thousands of details, advanced project.
Yes.
So I'll make some explanation to audience accordingly in Turkish first. Because this advanced topic, it requires mineral processing knowledge, flotation knowledge, USIM PAC knowledge, and modeling knowledge to digest all of the information. So yes. I'll just explain, in a easier way to audience. değerli katılımcılar, yani gördüğünüz gibi konu onu özellikle sordum. 3 küsür sene sürmüş bu çalışma. 3 küsür senenin muhtemelen çok özet olmayan bir hali. Yani çok, hani şüphesiz ki çok çok değerli bir çalışma. Onu dedim biraz önce. Yani bu çalışmayı enine boyunu anlamak için hem cevher hazırlama bilgisi, hem flotasyon bilgisi, hem bir program bilgisi, hem özelinde modelleme bilgisi gerekiyor. İşte randıman denklemlerine o kinetik parametreleri nasıl adapte ettikleri veya iyonik ne denir? İyonik mukavemet, iyonik mukavemete denklemlere nasıl entegre ettikleri, modelleri nasıl kalibre ettikleri çok hepsi apayrı bir konu. Ben şöyle bir öneride bulunacağım. Yani bu gerçekten değerli bir konu. Avrupa Birliği projesi, Horizon projesi olarak desteklenmiş proje. Arzu edenlerle, yani özel konuya ilgili olanlarla sonrasında daha detaylı belki bir şey yapılabilir. Toplantı yapılabilir. Çünkü bu sürede sadece hani belli kavramları anlamak mümkün. Onun ötesinde detaylı anlamak gerçekten çok zor böyle konuları. Dilerseniz öyle bir yöntem izleyelim. Birkaç sorusu olan var. Onların sorusunu aldıktan sonra Metin Hocam, bir soru var. Bir arkadaşların soruları nasıl şey yapalım? Etienne,
Siz devam edin Tuğcan
okay,
Hocam. Sizin
what,
alanınız.
tamam. Etienne, what I propose, this is I mean, long study with several details, including calibration, including ionic strength, effect into your even recovery, parameters and all. It's not easy to digest in once. So what I offered with directly person of interest, we can make another, more detailed or at the same detail, but longer sort of training or presentation. After this meeting, they can write about their interest. But there are some questions, as you can see. Let's ask you about the questions. Okay, there is one question from Juan. Any case study on lead zinc concentrator? One Aleka Tiagi, it's a question. Lead zinc.
Not yet, no.
Not yet.
We don't have lead.
Okay, Aleka, not yet. You saw. Somot Stefania. Okay, this is thank you. Oscar Ogala, can this software be used in simulation of wastewater from crude oil processing plant?
Alors, could you repeat again, please?
Yeah, wastewater, processing wastewater and crude oil.
We can embed crude oil. That's not a problem. That's the phase model of USIM PAC is very permissive. That's up to the user to define. So we can define a component of the water that is crude oil, or a phase crude oil also, because it depends on the way we want to treat it. But this can totally be embedded in it. And if we know that crude oil has an impact on flotation, if we can integrate this in the same way as we did for sulfate or calcium, that's totally possible.
Yeah. Oscar, in addition to that, in USIM PAC, you can have chemical equations.
Yes.
You can integrate these equations into software. So any equation you can define and you can integrate in your processing. Or what else?
Yes, we can integrate, and in fact, we didn't got into the details, but mineral dissolution model is based on chemical equations. Here we define very simple equations saying gang dissolves into sulfates to some extent, or into magnesium. We didn't have this, as I said, this is not the same approach as on thermodynamics when we would have we define minerals that dissolved. Here we can dissolve, just saying gang will dissolve in magnesium or sulfate. But these are chemical equations that are behind this, and the user can define his own equation also. Yes, that's totally free.
That's for sure. Arkadaşlar yani özetle dediği bu USIM PAC programında basit şekilde arayüzden kimyasal denklemleri tanımlayıp yani hangi molekül, hangi element neyle tepkimeye giriyor, ne oluyor onu tanımladıktan sonra her şeyi yapabilirsiniz. Yani sadece yağ vesaire su değil. Yani iyonları vesaire her şeyi tanımlayabiliyorsunuz. There is one last question, Etienne, from Juan. This is the way to go in a plant. The water influence on flotation is very poorly understood. The influence of water in flotation. Metallurgists should do this balance every week or every month.
Totally agree.
Until they understand how ions, this is a long question, but I'll summarize. So he also asked for larger training sort of thing. If the water were characterized routinely, then we will not have long studies and calibrations will be all ready to use these models. Actually, his question is how to integrate influence of water on flotation.
No, that's a good remark, and this was an output. I didn't insist on it, but water characterization is the basis of this, to have good quality data with sampling and have good routine in a plant to gather this data, accumulate it, and compare it to the plant. Will provide the data set to make to try to understand how the water impacts flotation. In fact,
depending on the mineral composition. He just approving this method for water characterization. He says he's approving. Okay. In another one. Okay. Sorularınız varsa değerli arkadaşlar yöneltebiliriz. Yoksa teşekkür edelim. If there is no more question, we can thanks to him and then all goodbye. So they all thank you, Etienne. So I don't think so. There is more questions. I can't see.
Okay. Thank you. Thank you very much. Thank you.
Thank you for your time, for your research. Thank you for European Union to support this very nice project, Horizon 2020. Very good. Değerli arkadaşlar, herkese çok teşekkürler. Metin Bey buyurun. Metin Hocam sağ olun. Teşekkürler.
Estağfurullah. Biz teşekkür ederiz Tuğçan Bey. Güzel bir sunum, güzel bir etkinlik oldu.
Hurşit Bey'in bir sorusu var.
Braak, thank you.